Hello everyone, welcome back to Alkaline Hydroxide 784, and today we will be covering electric fields. I realized that audio and video at the same time doesn't work, so the video became unusually long last time. I'm sorry for that. So I'm just gonna go back to what I usually do again. So as usual, I'll be going through the learning outcomes one by one, and hopefully it won't be 50 minutes long by the end of it. Alright, so basically electricity and magnetism is the section. Sorry, the topic is electric fields. So in electricity and magnetism, there's electric fields, current of electricity, DC current, circuits, and electromagnetism. And even though they have some kind of connection, they each cover slightly different things. So just realize that they are all actually connected, like how the oscillation, wave motion, and superposition is connected, but they all cover different things, Yeah. So in electric fields, we will be looking at how the electric fields work. So this topic is quite like gravitational field, gravitation, that particular topic, but applied to the electricity kind of thing, electric field instead of gravitational field. Okay, so the first learning outcome is what exactly an electric field is. Well, it is one of the force fields, in the sense, a field of force, which you can't really see because yeah, it's a force. It's not some light or something. It's literally a field of force, and in the field, there's at any particular point there is a field strength. So you can actually measure the electric field strength in a way. So at that point, the electric field will be the force that's exerted per unit positive charge placed at that point. This was written in the learning outcomes. Even the learning outcomes tells you how to write definitions. So if you just write it like this in your exam, it should be fine. You just say that the electric field strength at a point is the electric force exerted per unit positive charge placed at that point. The reason why it has to be a positive charge is because we just consider that as the default, in a sense. So that's just how definitions work. So we can, if we were to consider a negative charge as a default, our equations might be a bit different. But we consider the positive charge as the default unit that we're looking at. So yeah, great. And of course the unit is quite important because you're dividing by something. You cannot have it like, you cannot have something that's like 2 instead of 1. You know what I mean? It has to be that 1 unit. Yeah, that's how the definition works. Please remember those things. So next learning outcome is how you represent the electric field. Right, so of course you can't really see it. So how do you actually visualize the field? In A levels, they just use field lines because we don't have any fancy computer software to, do all those cool color gradient 3D things. No, we don't have that. So instead we use some lines, good old fashioned lines. So, well, field lines are like those, you know, they just show how concentrated the field is at that point. So if you draw more lines, it's more concentrated. If you draw lesser lines, it's less concentrated, I guess. But the more useful purpose of it is to show the direction of the field. So if you put like an arrow on the line, you can tell that it's going in a particular direction. Yeah, that's pretty much it. Yeah, so just use field lines to represent the field. I don't think there's anything much to tell here. Or if you see a question with field lines, you know what that is. You don't think it's some random chess game or some board game that you need to play, but instead you know it's a bunch of lines that represent the field strength. Or the field for that matter. Okay, so the third learning outcome is the analogy between electric fields and gravitational field, like the similarities in a sense, which we have looked at before, but I'll look at it in greater detail now. So in gravitational, and while doing that, we'll also cover some of the equations that are in the subsequent learning outcomes. So in gravitational field, we have the force, first of all, right? The very first thing that we learn is the gravitational force, which would be the big G times big M, small m, or r squared basically. So in electric field, what you use as your force? Well, in the electric field's topic, you had to take note that it's not just r at the bottom or r squared at the bottom. There is an extra thing there at the bottom, which is called 4 pi epsilon naught. Is it epsilon? I don't know. That thing that looks like a little e with a naught below it. And that the value for that is inside your data list, I guess. It's called the permittivity of free space. I think so. I think that's what it is. So just use that value from there. I don't remember what the value is, so don't ask me. It's some weird number. Okay, so in electric field, your force is equals to charge 1 times charge 2 over 4 pi epsilon naught r squared. So like the gravitational field, it is proportional, that inversely proportional to r squared, like the distance between the two charges. And yeah, in here they just represent them with q1 and q2. And the difference between gravitational and electric fields is that there is both a positive and a negative charge here. In gravitational field, you tend to see a lot of negatives in front of the equation itself, because gravitation is merely an attractive force. Gravitational force, I mean, yeah, it's attractive. But in electric, the electric forces can be both attractive and repulsive. So here we don't need to put any negative signs in front, and we just let the charges determine whether it's positive or negative. So this formula, force equals to q1 q2 over 4 pi epsilon naught r squared, is for the electric force between two point charges in a free space of air, in a sense, or air. Because in gravitational field, we look at spherical bodies, right? Here also we are looking at, we imagine them as spherical little points that emit, not really emit, but exert electric force onto each other, in a sense. Instead of something that's uniform, it's more of like a circular. Out as it goes out, the force decreases with with regards to r squared. So that's for two different 2 point charges in free space or air or whatever. So now let's look at the next thing, which is the field strength. So in the gravitational field, we look at field strength in terms of the G, right? So well, G would just be the force divided by the mass, one of the masses. So usually it's the smaller mass, because you're looking at the force acting on the smaller mass. Usually that's how it works. But of course, the field strength that acts on the bigger mass is quite different already. So you're looking at the smaller mass. So here it depends on which charge you're looking at. So you remove the charge that you're actually looking at, in a sense. So if you're looking at a point charge in free space, then you remove that particular charge from the equation. So in gravitation field, you would get G equals to big G, big M, or R squared. And in electric field, you would be getting what we call E, which is the electric field strength, E, big E, is equals to Q, which is probably the charge that is inflicting the strength, over 4 pi epsilon naught r squared. Okay, so the electric field strength is based on a point charge in free space or air, and I think once again it's probably a positive charge, or I mean, yeah, that's how it works. Or a negative charge also, I guess. I don't know. So yeah, it's very similar. It's just that you have the same 4 pi epsilon square. That's the difference. That's the only difference here. And there's no G in this thing. Like the big G, they don't have big G in electric field. They instead have 4 pi epsilon naught. Yeah. Okay, anyway, that was pretty pointless to say. Okay. So the next thing that we'll be looking at is the okay, in gravitation field we have the potential as well, right? So we have the gravitational potential and the gravitational, like the gradient of it, in a way. What was that thing called again? The Wait, sorry. Gravitational. What was I thinking of? I don't know. Never mind. So yeah, we have the gravitational potential, and then we have the gradient of the gravitational potential, which I don't remember what it's called for some reason. I don't know why. Nah. Oh yeah, but gravitational potential energy. Sorry, I'm in. I'm pretty. Okay, never mind. Okay, so for for gravitational potential, we have it is actually G, big M or R, right? So in electric field, for the potential, we have something called V, the thing you use in your electric circuit, that V. And V will be equals to big of the Q or 4 pi epsilon naught R. So that's pretty similar too. And if you look at energy per se, I'm not sure. Okay, we would be able to calculate an energy in some questions, so do take note of that. But if you're looking at energy, gravitational potential energy would be big G, big M, small m, or R, I guess. And in electric field, it would be pretty similar. It would have the energy equals to both of the Q multiplied, Q1, Q2, or 4 pi epsilon naught R. So it's very similar. That's how you remember two topics in one. Just remember the differences and everything else is similar. Okay, so now let's look at the stuff that's actually pertaining to this topic, which isn't really as covered in gravitation. So let's look at the scenario where we have a uniform field rather than 2 point charges, because all the comparisons with gravitation field is based on electric field having 2 point charges rather than a uniform field. So how do you get a uniform field? I mean, you don't want to have any circles involved in the sense. You don't want your field lines to look like to you know I mean your potential lines to look like circles. So if you want a uniform, wait, is it potential line or field line? Okay, never mind, I'm confused. Okay, so uh just ignore what I said. Okay, so yeah, if you're looking at a uniform field, you would need to use something that creates a you know, parallel kind of potential line in the sense. And therefore we get parallel plates like metal plates or something, and you connect them to a battery or a power source. And in that, if you do that, you get one side that is positive and one side that is negative. When you do that, you will get a particularly uniform field, for the most part at least, in a way. But it will be more uniform in the center of the plate compared to the outside of, like, the edges of the plate. So if your plates are, let's say, like, okay, if I draw them vertically, like two vertical lines, and I would be drawing a field that is perpendicular to the two plates, and the potential is parallel to the plates. That's what I meant by field and potential lines. So the field will be uniform because the gradient of the potential change is quite uniform within the two parallel plates. So the potential will keep changing as based on which point you're at, but the field will be the same throughout the entire plate, except maybe at the edges. So how do you look at this? Since I mentioned potential gradient, that's actually how you look at it, because the field strength is equals to the gradient of the potential. As you have seen, you should look at point charges, right? The field strength is Q over 4 pi epsilon r squared versus the potential, which is Q over 4 pi epsilon r. So the field strength is just potential divided by r. So if you apply this to a uniform field, then instead of r, we use a d, like a small d, and that's the distance between the two plates. So in this scenario, the field strength E would be equals to potential V over D, and therefore V is equals to E times D. So that's the equation that you need to know here. So let's say if the plate on your right is plus 10, V, and the plate on the left is -10, then the field strength would be equals to 20 over D, kind of, because the difference is 20 and the difference in potentials is 20, and the D will be whatever D that you get, or whatever that I write down on a piece of paper. I don't know, maybe it's like 1 meter, then it's like, I don't, yeah, kind of depends on how you write the units as well. So to be like 20 volts per meter or something like that, kind of. So yeah, now that you know how to do it, you can just, you know, you can move on to the next learning point, I guess, learning objective. Okay, so how do charges behave in uniform fields then? Since you already looked at how charges work in a circular-ish kind of field, or not really circular field, circular potential line kind of field, you look at how charges work in a uniform field. So let's say instead of vertical, we now make the two plates horizontal, so it's a bit easier to visualize. And we shoot this, I don't know, charged particle through the center. Where will the charged particle go? Well, if it's positive, it will go towards the negative plate. If it's negative, it will go towards the positive plate. And therefore, the charge won't be in the same it won't be in the same axis. It will be moving upwards or downwards based on, you know, where the plates are and what charge it is, in a sense. So the force, yeah, the force is basically based on the electric field strength, and it will be constant throughout this entire period of time for the particle until it hits the plate, I guess. So it is possible to actually think about it as the charge having an electric force in one direction, if the direction is upwards for that matter, and its mass bringing it in the other direction. Well, of course, usually its mass is so small that the weight isn't that big either, and it doesn't really make any big difference. So the majority force is just the electric force acting on the particle. So you look at this concept again in terms of magnetic force as well, because that has more variables and is a bit more likely to create some kind of balancing equation in a sense. So yeah, that's how it works if you shoot a particle through this uniform field. Okay, so the next learning point is the electric potential at a point. And okay, I mean, you can, if you want to look at the definition part of it, we already looked at the equation, which is basically just Q over 4 pi epsilon naught R. But if you want to look at it in terms of the definition, in gravitational field, you have the gravitational potential as the work done per unit mass of, you know, in bringing the small test mass from infinity to a point. And electric potential, you can say it as the work done per unit positive charge. Remember the positive, in bringing a small test charge from unit infinity to that point. So just think of it in the same way as you think the gravitation field, but okay, since you can't really think of a hand opposing it, just think of it as, you know, let's say if you have a positive charge, depending on what the field is, the force will be either attractive or repulsive, and if it's attractive, you're trying to resist it, so the work done will be negative. If it's negative and the force is repulsive, and you know, you're allowing it. Wait, what am I thinking? Okay, yeah, the force is attractive, you're trying to prevent it from going there quickly, right? So that's the work done is negative. The force is repulsive, and it's trying to go away. You're bringing it into the point instead. You're actually doing work because you're forcing it to be in that point. You know what I mean? Yeah. So that's how it works. So just use the equation to figure it out. It'll be a lot easier to do it with the equation. So the field strength of the electric field at a point. Oh yeah, that's what I mentioned just now. The learning outcome itself says that State that the field strength of the electric field at a point is numerically equal to the potential gradient at that point. I already told this, so we're done. We finished all the learning outcomes. So, and it's not 50 minutes long. I hope you're happy. Yeah, okay. So yeah, to conclude, I think this topic shouldn't be very hard to do because it's actually just like kind of regurgitation of the gravitational field with some extra enzymes added into it. If you understand what I mean. Never mind. That sounded weird. Okay. So it just it's just like the same ish equations applied in a different context. The only extra thing is the uniform field here, so just know how that works and you're good. You'll be fine. No issue. The main problem in this particular section is more of the later topics, especially the magnetic ones, because oh my gosh, the definitions are annoying to remember. They're really long. So yeah. But yeah, I guess this particular topic isn't that hard. It's very easy to explain, I think. At least for me, it seems easy enough to explain. So I hope you found this video useful and at least somewhat more clear than whatever I was mumbling last time. And if you did find this video useful, please press the like button and subscribe. And with that, I would like to say thank you and bye!